Very good. So now, just now during the break, I had the discussion with Kunara regarding the workshop which he has planned for tomorrow. That workshop is going to be on Simulink. Okay. And before that workshop, what Konara has advised me that he want to have 1 hour lecture with you, right, to get to motivate you and to get the or to provide more inputs to you how to use the Simulink, which type of examples he is going to take into account, how those examples are going to work, means like how the technology or how that system is going to work. So I believe that in within a 5-10 minutes he will join us, okay, and we will continue. Then he will continue his presentation or for tomorrow's Simulink workshop, okay. And then because anyway we have this 2 hours training or the let's say project practice work, so Konara will also be available during that time period also, or we can use that period something like matching, so can have, so to have more discussion with all of us for identifying some project task and discussing also like whether you are able to follow or not and like that. Is it okay? Good. So maybe I think I will just go, I will skip couple of slides, or maybe I will just go to the next slide, then you will go. So now you can see with reference to this slide what we have seen, okay, we have many different options, like this is a very high level, okay, many different options, like if it is a wind turbine, then the power conditioning device and the controller, it needs to work in a very different way because the operational characteristics are quite different. Similarly for the photovoltaic also, similarly for this distributed generator also, energy storage also, and for energy storage basically then it is not going to need bidirectional controller here or bidirectional energy flow management, okay. So Konara is going to take a typical case in the Simulink for photovoltaic, let's say. So for that, and that is going to be unidirectional power flow. Okay. So for that unidirectional power flow, here what we have the power controller, let's say power conditioning unit. So basically we are going to use DC to DC converter, and that DC to DC converter, it is also going to have the maximum power point tracking mechanism also. And based on this DC to DC converter, and then connected from DC to AC converter, so that we can inject the power at the required frequency and the voltage to the grid. Okay, so he is going to show us like how that control loop is going to provide the control signals, especially to the DC to AC inverter or converter, that going to produce the required amount of voltage, means fixed amount voltage value, okay, and at a rated frequency, okay, then injecting the power, means basically the current, okay, into the network. Then another point he is also going to discuss here, we have the variable source, right? With the variable source, like all the time the power output is going to be changing, okay, due to the solar variation into the solar radiation. Therefore the maximum power point is also going to change. That maximum power point is going to be managed through the DC to DC converter here. So when we are managing that DC to DC power converter, and that operational voltage and the operational current are going to change due to the input into the solar photovoltaic, right? Therefore the input to the DC to AC inverter here, that is also going to change, but we want to have the output at a fixed voltage and at the fixed frequency. So for that purpose, how we have to do the control mechanism in a simple way of the grid injection of active power from the photovoltaic system to the network. So he is going to cover that in tomorrow's workshop. So in few minutes of time, when Konara will log in, then he will provide you much more information on this point, right? And based on that, we will continue for tomorrow's workshop. Okay. So then, coming to the overview, right? So there you have seen that we need to have very different type of equipments, right? For that, we cannot replace all the utilities components, right? So we have to find out how the power conditioning devices or the components related to the integration of different type of technologies, right? How they can operate seamlessly, how they can operate seamlessly within the existing network, that we have to study, that we have to study also. Then another very interesting thing, like we talked about information communication technology. So let's say we want to utilize the existing communication facility, for example, the 3G facility or 5G facilities, that then IT company has to integrate into the system. And then of course, then we have to work on how we are going to communicate to the with the consumers about the benefits of the smart system. Then this is a very interesting point. Okay, so that point here you can see that in every substation, if we take from the bottom side, right? If we take from the every substation, right? Within the substation, there is going to be a lot of distributed generators, energy storage, controllable loads, and so on and so forth. So for everything, there is going to be some intelligent function agent. So that intelligent functional agent, how is it going to work? With actuators or the sensors also. So here you can see that in one station, there is going to be a lot of intelligent functions and actuators or sensors. And such type of small substation, that we can call it as a microgrid also, but they are also going to communicate or manage with another neighboring microgrid also. And on top of that, then we are going to have the control area, where we are going to have again the different type of intelligent functional agents, and then the one control area, let's say, so let's say the C1 area, and then there is going to be many control area. So that, let's say here K control area is there, so that units of intelligent functional agents for each area going to be for kth till the kth area. Similarly, for the microgrid or substation S1, let's say for example, so here let's say if we have the substation till Sn, okay, so many different intelligent functional agents are going to be there. Then if you go to the upper layer above the control area, then we are going to have the regional area. That is, let's say this is the region R1, for example. So then similarly here also there is going to be a lot of functional agents, and these functional agents then going to get the information from the control area C1, and the control area C1 is going to get the information from the substations area here also. Then on top of that, then we are going to have the main grid. Okay, so main grid, then it is also going to have many functions are going to be there, and for each functions then functional agents will be there. Okay, so for different functions, so this different functions, for example, voltage stability, frequency stability, power quality, interconnection issues, and many things are going to be there. So here you can see that all the things, they are interlinked with each other. Okay, so the interlinking is very important, because to get that data or to get that information, for to have this real-time operation, real-time appropriate operation for managing the system stability and dynamics, okay, that is very important. So here, that's why you can see that this side, it has been taken as a integrated messaging or the data. So this infrastructure for distributed autonomous intelligent agents are going to be required for the smart electrical energy network. So here you can see that how complicated it is going to be, right? So based on your interest and based on your expertise, now you can contribute or to do the research work on any of the part of the smart grid. Okay, that is a very important part. from the learning point of view, but at the same time, being the student, you need to have the overview of the high level information of the operation of the smart grid also. Then here we talked about the intelligent systems, okay, and then control area, region, and the grid area. So, and we are going to have the different actuators also in each substations. So these sensors, okay, or the actuators are going to collect the information in a some particular time interval. Some of the information may be collected at the millisecond or the microsecond level also. Some of the information may be collected till the few seconds of level. Some of the information may be few minutes, and some of the information may be the few hours also. So depending on which type of information have been collected here in this through these intelligent agents, and how it is going to be used for controlling the system, either for the primary control, secondary control, or tertiary control of energy system. At one point, we will study that how the primary control it works, how the secondary control works, and then how the tertiary control works. This primary, secondary, and tertiary controller concepts or dynamics, or let's say algorithms, okay, will be, I mean, you can understand them when we are going to cover some significant part in ENE411, because that ENE411 is going to provide much more technical depth in this course. Okay, so coming back to the time stamping, so here we have taken the faster cycles. So faster cycles are defined when those are below 2 seconds, and slower cycles are defined as 2 seconds and over. So here you can see that we have the some 10 millisecond cycle, 100 millisecond cycle, then let's say we have 1 second cycle. Let's start with the 10 millisecond cycle. 10 millisecond cycle, it is quite a short period of time. Within that short period of time, that frequency deviation and how the stored kinetic energy of such type of conventional generations are going to be used, okay, those points are going to come here in this 10 millisecond cycle, okay, because we want Earth Power Supplier Company, they have the accountability that they should provide the power quality of a very good level. So that power quality means, let's say below 10 millisecond level, right? It means that the frequency deviation should not be there. So we are going to get the 50 Hertz cycle per second, for example. So in 50 Hertz cycle per second, right? So in 1 second of time, 50 Hertz cycle, right? 50 cycle per second, right? 50 cycles should be there. So there should not be any deviation, right? If suppose there is any deviation due to the load fluctuations, and that fluctuations may happen due to the intermittency of renewable energy sources, or maybe due to the load dynamics also, then this rotational generator, right, is going to provide that stored kinetic energy. That is how much stored kinetic energy is there. It is going to depend on based on the rotational mass or the moment of inertia of the system. So that information is going to come here in this period of 10 millisecond cycle. That this 10 millisecond cycle, that inertia release within the few seconds of time, right, we will study in the ENE411. Okay, so there you can see that how the important thing is that. Then of course then there will be some delay. Let's say then another cycle is coming, 100 millisecond cycle, 100 millisecond cycle, right? And this 10 millisecond cycle is going to provide the input to the 100 millisecond cycle next level, okay, and then let's say that deviation is not able to fulfilled by the stored kinetic energy of the rotating mass, then another controller or another loop has to come into figure, and then it will change that how much it is going to require. So then it is going to provide for the forward input to this cycle or to this controller also. Similarly, then we are going to the another second, that is a 1 second cycle. So all these are going to come under the primary control mechanism, and some of the information then here from the secondary control mechanism is also going to come here. In the secondary control mechanism means especially at this level, 2 second to 1 second level, right? So especially this 2 second to 1 second level, that we are going to change the input power to the turbine, okay, so that whatever the deviations are happening, and if those are not able to fulfill with help of the stored kinetic energy or moment of inertia of the rotating system, then we have to increase the input fuel or the water flow or the steam flow or the gas flow to the turbine and manage it, right? So that is going to be the secondary controller, okay, that we will study in much more detail in the ENE 411. Now let me see if the Kunara is there or not. Hello Kunara, are you there?
Yes. Hello, Professor.
Yes, yes. So Kunara, shall I stop here and to give you the control now? Then you can
Okay.
You can make them ready for tomorrow's workshop.
Yeah. That's true.
So students, so now I'm giving the control to the Konara, okay, and then Konara is going to, I'm making him a host now, okay, just a minute, I'm making him the co-host now, okay, and then Konara can share the screen with you. I'm stopping sharing my screen, okay, and then he can make you ready for tomorrow's workshop, okay. So Konara, please go ahead.
Yeah, okay. Thank you, sir.
You can start your video also, or you can share the screen, no problem.
Yeah, I will share my screen.
Yeah, it's fine. Yeah.
Okay, we'll see. Can you see my screen?
I can get Microsoft Whiteboard.
Yes. So this one.
Yeah.
I'm using this one.
Yeah, Microsoft Whiteboard I can see.
Okay. So hello everyone. Tomorrow we are going to have our second workshop for ENE506 Smart Grid course. For that, we need to give you some overview of renewable energy systems. Actually, tomorrow what we are going to discuss is on photovoltaic systems, control strategies related with the photovoltaic systems using Simulink, MATLAB Simulink. So tomorrow we are going to discuss on snapshot analysis, not time series analysis. In the last workshop, we analyzed techno-economic sizing of a renewable energy system or a smart grid system. So tomorrow we are going to discuss on dynamic aspects of renewable energy or a smart grid systems. So in the first workshop, we are going to discuss on photovoltaic systems. So we are going to start from the very beginning to give you some very good overview and very good insight. So here I can tell you, if you consider a PV system, let's say if you consider a PV system, something like this. Can you all see what I'm writing?
Yes, I can say Konara.
Yes, okay.
You have written PV system, yeah.
Yeah, okay. So then it's okay. So here, so this is the PV system. And then when you come to PV system, basically we can consider two topologies. That is, here you can see the AC bus, and here I'm going to connect a load. So this load is solely supplied by this PV system without a support of grid. For this type of system, we term as standalone PV systems. And when you have the grid, so here you have the grid, and then this is known as grid connected PV system. So why I'm going to start from a very beginning, because the control strategies adapted here and here will be different, because we are going to consider with this workshop, we are going to consider about the control strategies. Control strategies adapted with the grid connected system in some cases will be different from the standalone system. So that is the starting point. That means when we are analyzing photovoltaic systems, we have basically two topologies or two modes. Actually, when we are dealing with grid connected photovoltaic system, with the unavailability of the grid, this system will switch to the standalone mode. Therefore, when you are analyzing a PV system, we have to consider about these two basic topologies. And then, before going to the control strategies, we should understand another two basic operation of this PV system. For that, actually, I will, for our discussion, I will consider this, I'm going to consider about the grid connected PV system, because in tomorrow workshop, we will consider the grid connected topology. So when you come to the grid connected topology, so here I will just explain. Here you have the let's say PV, and this PV panel will be connected to DC to DC converter, and the DC to DC converter will be connected to a DC bus, and this DC bus will be connected to the AC bus through an inverter or a DC to AC converter. So this is our AC bus. So this is your AC load. That means the load which is connected to the AC bus is known as the AC load. And here also, if you want, you can connect loads. That is DC load. So our grid will be connected to here. This is the grid. So if you consider the power flow, I'm just here, PV, the solar, inject the power to the DC to DC converter and then to here, but to the DC bus. But there is no any power flow from the DC bus to the PV panel. That means the power flow from DC bus to PV panel should be avoided. Only power flow from the PV module to the DC bus. Therefore, this is unidirectional power flow, and this converter is known as unidirectional DC to DC converter. You study these things with Professor Mohan, but I am here explaining just to give you overview and how to model these things in Simulink. So here, this actually power flow can be in this direction, and also the power flow can be in this direction as well, because from the grid, power can be flown to the DC load as well. Therefore, through the inverter, power can be flow in this direction and also in this direction. So therefore, here you should note the power flow in bidirection. So this is known as, these two are power electronic converters. So this is the system topology. That means basically we are having a PV module and unidirectional DC to DC converter. And
I missed to record my lecture, but you should click the record button on your lecture.
Okay. Okay.
Yeah.
Recording in progress.
Okay, so is it being recorded?
Yeah, I think now it will start recording. Yeah.
Okay.
I missed my to record my lecture because some of the students, they may not be able to hear, so they may want to see it at a later stage. Okay, carry on.
Okay, so here we have the unidirectional DC to DC converter, and this is the DC to AC inverter, or else we are saying this as voltage source inverter, VSI, voltage source inverter. And here you have the grid, here you have the AC load, and this is your DC load. With Homer, what we did was we size this PV module and the grid component. That means in the workshop one, what we did was, so we knew this AC load or a DC load. For the easiness, I'm just taking these two components as load. So then we know the PL. that is the load power. So we know the this PL, the load profile. While knowing the load profile with Homer in the first workshop, what we did was we analyze and we plan the size of this PV system and some aspects of the grid. Here we are going to study about the control aspect related with this system. The control aspects related with this system. So actually, when you have this system, we have basically two control topologies. The first one is maximum power delivery, and the second one is dispatchable operation. So we will have a look on these two control strategies. So here I'm just taking here the load power should be supplied by grid power plus PV power. So this is the very simple equation. So here, if you consider the global tilted irradiance, that is the irradiance on the PV panel, and then I'm consider a situation where the load power is 250 kilowatt, and the max, that means the power incident on the PV panel, I'm just taking 200 kilowatt. So here it is 200. So to supply this load power 250, the grid has to supply 50 kilowatt. Then the load power will be met. And there is another situation that means in a very sunny situation, your global tilted irradiance power will increase to 240 kilowatt. Sorry. So now the PV power is 240. Then to supply this 250 from the grid, we need only 10 kilowatt, because PV panel is supplying its maximum power to the load. And let's say due to some shadow or something like that, our power reduced to 150. So PV power reduced to 150. To meet the load power 250, we have to, that means the grid has to provide 100 kilowatt. That means here you can see the PV power, the PV module inject its maximum power. So this is the maximum power. So based on the grid will compensate. The grid will compensate so that the required load demand will be met. So this operation is known as maximum power delivery, because the control strategies related with this topology will be differ from the topology that I'm going to discuss while after a while. Okay, so that's why I'm just specifying these control modes. So this is known as maximum power delivery. That means the maximum power available at the PV panel, the PV module will be injected to the grid. So based on this maximum power, the grid will be compensated. There is another situation That is, the second one is, so the second one is dispatchable operation. Here in the dispatchable operation, you have similarly, this is the P load, and this is our PV system power and the grid power. Not like in the maximum power delivery, during the dispatchable operation, the grid will specify for the PV system during this specific period, you are supposed to provide this much of power. Let's say from 10 a.m. to 12 noon, our our PV system has to provide 200 kilowatt. So the load power is 250. Then to meet the load demand, the grid has to provide the remaining 50 kilowatt. But here it is okay for this situation, because the maximum power is 200. Here the maximum power is 200. Because of the maximum power is 200, there is no any problem. But when you come to 240, now the global tilted irradiance will be increased. Now the power is 240. But our constraint is we are not going to inject this 240. Out of this 240, we have to give only 200, not 240. In this case also, here even though it is the maximum PV power is 150, but from the PV system we'll have to deliver 200. Therefore, in the dispatchable operation, here the power is, active power is always 200. In the maximum power delivery, we are injecting whatever the maximum power available at the available on the PV panel. So why I explain these two simple things? Because the control strategies and the topologies we are incorporating will be different based on the operation, maximum power delivery operation and the dispatchable operation. So did you understand the difference between these two? How about the feedbacks? Okay.
I think it's quite okay, good.
Okay.
What I feel, Kunaran.
Okay, sir.
Yeah, yeah.
So,
and then basically the student has to give their feedback, or I mean, not the feedback, but if they have any doubt or if they have any questions also.
Okay, yes.
They should feel free to ask, okay? Because we are in the virtual mode.
Yeah, we are in the virtual mode.
Yeah.
So, so far I explained we are going to construct our PV system in basically two operations, that is maximum power delivery and dispatchable operations. Tomorrow we will discuss on this maximum power delivery, the control strategies related with maximum power delivery. Actually, when you come to this control related things, it is not just easy like Homer things. So therefore it takes time. Okay, so that's why we are giving this overview. In another workshop, we will discuss about this dispatchable operation. So now, now we understood that there are two two mode of operation. One is the maximum power delivery, and other one is the dispatchable operation. So here the interesting thing is during this 150, okay, let's say in this 150, now the maximum power available at the PV panel is 150, but the load from the PV system you have to inject 200 kilowatt. Therefore, to compensate the remaining 50 kilowatt, we have to have another power source. Usually, we use a battery system. So for the battery also, the situation is same. You have the DC to DC converter. And it is connected to the DC bus. And here it is DC to AC converter will be connected to the AC bus. Not like in the PV system, here the power, that means the power can be delivered in this direction. That means when, I mean, in this particular case, the PV system provide 150 and the battery provide 50. So therefore power delivery is in this direction. But during this situation, 240, you need to provide only 200 to the load. The remaining 40 can be stored in the energy storage. So therefore, the power can be in this direction and also in this direction. So therefore, this converter is bidirectional DC to DC converter. Here is again voltage source inverter. So this is the basic topology. This is the basic topology that we are going to study. Not in tomorrow. Even tomorrow we won't be able to completely discuss about the control strategies related with the maximum power delivery situation also. Tomorrow we'll just start the control strategies related with this operation, and with the time progress we will build up your knowledge. So as an overview, these are the two basic operations we are going to discuss in our workshop. So when you have energy storage along with the PV module, then this mode of operation can be considered as dispatchable operation. So here, not only here your battery, not only a battery, if you want, you can use a supercapacitor also. When you use a supercapacitor, the energy storage is known as a hybrid energy storage. With the supervision of Professor Mohan, we have published one article, the control strategies related with hybrid energy storage. So as a reference, we can give that article for you also. as I think Professor Mohan taught you, that when you come to control strategies, we have primary control, secondary control, and the tertiary control. So when you come to smart grid control, in here we are going to study only primary control. Using Simulink, we will study only primary control. So up to here, I explain the topologies. That means at the very beginning, I explained that we are having two basic topologies, that is standalone PV system and the grid connected system. So in the grid connected system, I mean, then I'll come to the point that I was supposed to explain a little bit later. As a control, what we'll have to do is we have to control these converters, power electronic converters. We have to switch these, we have to control the switching of these power electronic converters. As control, that's what we have as primary control. That's what we have to do. So here 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 this is the DC side and this is the AC side. Here you have DC control. Here you have AC control. Since we are going to generate this AC signal using this voltage source inverter, we name this as VSI control. Okay, so to this control system, usually we take the parameters of this VDC and IDC output, and based on and some parameters here also, maybe IPV, VPV, I battery, and V battery, and we take these inputs and to this controller, and we generate the PWM signal to these power electronic converters. And here also we are taking the inputs from this AC bus, that is VABC, IABC. Why I'm using this ABC? Here the supply is three-phase. So here the supply is three-phase. So therefore you have VA, VB, VC, IA, IB, IC. IA, IB, IC. So you have to note that I have used small case letters for AC and capital letters for DC. And here are the frequency also, maybe phase angle. We have to take these things as inputs, and then we can generate the PWM signals for the controllers, sorry, converters. So that is the basic task that we are going to perform. When you come to control, we have basically two types of control, DC control and the VSI control. If you are interested in DC control, you can analyze DC control. If you are interested in AC control, you can analyze and you can work with voltage source inverter control.
Konara, so
Yes.
here maybe I would like to tell to the students.
Yeah.
Let's say here, if we go to the DC control side, there are many different type of functionality which we can see. If suppose if we take PV and here only the DC to DC, okay, and to the DC bus, then here this controlling of DC to DC, basically that is controlling of DC to DC converter, right? Either it will be mostly it will be in the boost converter mode, but we have to see that the operating point, how it is matching with the maximum power point of the photovoltaic system, right? So then to control this DC to DC converter, or basically the PWM signals, so they will be based on a different type of mechanism, for example perturbation and observation, or maybe some using some let's say real-time parameters from let's say the photovoltaic house solar insolation and operating characteristics and like that. And so those type of algorithms, okay, can be studied here when we want to implement them into this DC to DC converter control for maximum power point. Then similarly, then another control can be for the battery bank also. Then this is going to be the bidirectional, okay. And for bidirectional, then when we at some point we want to store the energy, some point we want to discharge the energy. So that charging and discharging DC control here maybe depends on the pricing mechanism also, or whenever we want, like when it is profitable or not. But at the same time, then this DC to DC control mechanism has to get the feedback from the energy availability at the battery bank or state of charge level also. So that also we need some input here for the DC to DC control also. So there are many things like which we can incorporate or study within the DC control. Even it looks like a very simple, but it is a very interesting here. And in the DC to DC control, depending on the type of battery, let's say whether it is a lead acid battery or lithium ion batteries, or let's say the supercapacitor also. So depending on their charging and discharging characteristics, we can manage the power flow or the energy flow with reference to the time from this DC storage from here to the network, and the vice versa, and how they can help to manage here the DC power flow on this one. So on the DC bus, then another thing is very interesting, that if we put some DC load, for example electric vehicle charging, then again we have to see that how this unit can be worked as in a decentralized charging station based on the photovoltaic and the battery bank also, because that is also going to be quite integral part within the AC network or the distributed network. Isn't it, Konana?
Yeah. That's true. That's true, sir.
Yeah.
So I think Professor Mohan gave a very good insight to the future work for you. Actually, why I have drawn this diagram is just to give you directions on different projects. Actually, here the DC control, it's just a rectangle. It's a small box, but within this box, you can perform a lot of things. As Professor Mohan told you, this is not very simple. Based on the state of charge and some other state of charge of the battery and the state of charge of the supercapacitor and the energy pricing, energy policies. All by taking all these inputs, you can perform a very interesting analysis in this DC control, under this DC control. Similarly, here also you can perform, that means here in the VSI control, you can perform a very interesting analysis. So in the second workshop, we will start with this DC control and the voltage source inverter control. So before going to the models, to increase your understandability, we are giving this overview, because if we are trying to just open the model and try to explain the parameters, it would not be very interesting for you. Okay, there are some